So welcome back everyone to this session. And there are two talks in this session. The first talk is by Kabir Ramola from TIFR Hyderabad, and he's going to talk about current fluctuations in interacting active lattice gas.
Thanks, Shubhro. It's a real pleasure to be here in a meeting to honor Deepak. So today I'm going to describe some work that I've done in collaboration with graduate student Steffi Jose, Rahul Dandekar, who's presently a postdoc at SIA, and my colleague Mustansir Barma, who are all in the audience. And a lot of this work is related to the work of Professor Kafi, who's going to speak after me. So he's also in the audience. So initially, I'd just like to tell you why we are studying this problem, because active particles, as you've already heard, are very interesting systems, and they are basically particles that can perform directed motion through self-propulsion, and they constitute a major class of non-equilibrium systems that are being studied in multiple different ways. And these systems break detailed balance at the local level, at the particle scale. And so many interesting questions arise in these systems. But some interesting questions that we hope to answer with simple lattice models would be, how does the effect of activity affect the particles, and the effects of exclusion versus activity? How do they couple? What happens near and beyond motility-induced phase transition? That is also an interesting question. And can fluctuations in phase and time behavior be studied analytically? In this context, it turns out that macroscopic approaches are quite useful, as they don't depend much on the microscopics of the system. And so in this talk, I will describe a particular kind of model which allows you to do some sort of macroscopic understanding of the questions that we are asking. So I'll just first describe the microscopic model. So this is a model, sorry, I should have put the reference here, which is, I'll just give the reference here. So it was sort of developed a few years ago in order to write down exact hydrodynamic equations. So let me first describe the model. So you have two species of particles on a lattice, plus particles and minus particles, and holes. Plus particles are biased to move to the right. Negative particles are biased to move towards the left. And so mu is the occupation number of each site. So mu and mu I plus 1 can exchange with some diffusive rate. So this diffusive rate allows you to move a plus particle to the right or a minus particle to the right as well. So you can basically interchange the particle indices of nearest neighbors. Similarly, you can have a bias rate, lambda, which is scaled by the system size. So it's weakly biased, where the plus particles can be, so plus particles can be biased to the right with this weak rate. Minus particles can be biased to the left. And lastly, you have this effect of activity, which is plus and minus particles can interconvert with some rate gamma, which scales again with the system size in a certain way. And so this, of course, describes RTP particles on a lattice. It also has hardcore interaction because only one particle per lattice site, except that it also has this microscopic diffusion in it, which allows you to move plus and minus particles through each other. But once you write down such a model, you can start to write hydrodynamic equations for this model, which was sort of started with this study in 2018, but has been developed over the last 4 years. In fact, recently, a lot of papers have been written on the fluctuating hydrodynamics of this model, which I will describe in detail. So you can do a diffusive rescaling of space and time so that you can actually write down hydrodynamic equations for coarse-grained density fields. So mu was the occupation number of site, mu plus is the occupation of whether there's a plus particle at that site, mu minus is whether there's a negative particle at that site. And you can sort of coarse grain over a certain length scale, L to the D, and you can write down density fields, which are the summation of the plus and minus coarse-grained densities, and magnetization fields, which is the difference between them. There are two different densities that you can define in this model because you have two different kinds of particles. And once you have this, you can write down coarse-grained hydrodynamics equations. So for the density field, it's quite a simple looking equation where you write diffusion, but with a bias term. And this accounts for both the bias and the flipping. And for the magnetization field, you have exactly the similar looking equation, but now you have non-conservative terms because the magnetization can actually go to 0. So if you start with an unequal number of plus and minus particles, then they will gradually sort of settle down to the same magnetization of 0. So these equations describe the system at the hydrodynamic scale. And so the question is, what can this predict? So recently, some work was done last year on understanding the phase diagram of this model. So if you take these hydrodynamic equations, one slide before, and write down when these equations are unstable, you end up with this phase boundary, which is basically the density and activity on this axis. So Peclet number, I will describe in a bit, is basically a stand-in for the activity. The more bias you have, the larger the Peclet number, and this is the density. So at a particular density 3/4, you have this sort of divergence, which I will describe. But the metastable states and unstable states that appear in this model are analogs of motility-induced phase separation. And so you can actually understand this phase diagram quite well. What I've colored here is something called the correlation length, which comes out of a fluctuating hydrodynamics approach to this problem. So I'll describe that. But for later use, I'll just say that the correlation length seems to diverge at this one point, which is the critical point, density 3/4, Peclet number 4, a correlation length diverges. So what do I mean by that? So we can next go to a fluctuating hydrodynamics framework, which was again developed last year. You take exactly the same equations, the hydrodynamic equations, and now you add noise to them. And so this is just the continuity equation for the density, continuity equation for the magnetization. As I said, there was a non-conservative term. So there's a non-conservative term here for the magnetization. But now this current is basically the hydrodynamic current plus some noise terms. And this is conservative noise in the density current. Magnetization current now has a conservative noise term and a non-conservative noise term. And of course, if you just put the noise to 0, you will return to the original equations that I provided in the previous slide. So these are the deterministic hydrodynamic equations that describe the current for these two fields. And the Peclet number is a very important quantity in active particle systems, which is the bias divided by the flipping rate and the diffusion constant, square root of that, to make it a non-dimensional number. Heuristically, it gives you the ratio of the distance traveled by pure bias versus pure diffusion between two consecutive tumbles. And so this basically tells you how much activity you have in the system. So once you've written down these fluctuating hydrodynamic equations, you want to know. So yes. Yeah, so this is a good question. I was just going to, yeah. So you write down So you write down the noise terms as a heuristic noise. So you have some current, which is the deterministic current, plus some noise term. Now you ask for how the noise is correlated. And in this, you can actually, this particular model, you can actually map it on to this ABC model where these noise terms are known. And so this, for this particular model that I'm describing, the correlations in the noise are not heuristic, but these are known exactly with a mapping to ABC model, which is a 3-species model. Usually in fluctuating hydrodynamics, you will write some heuristic correlations for the different density and magnetization fields. In this case, you can actually write down these equation 7, which is the exact correlations between the noise. And similarly, for the magnetization field, you also have tumbling, which is the Poissonian variable. And so, based on this framework, now you can sort of try to build something known as macroscopic fluctuation theory. Of course, you can use this to derive, for example, time-dependent correlation functions, density-density correlation functions in time, and so on and so forth. And all of that has been done in this study with Professor Kafri, who's in the audience. And they were able to sort of show that the microscopic simulations match very well with this fluctuating hydrodynamics framework. So the next step you would try to do is, once you have a fluctuating hydrodynamics framework, is go to a path integral formulation, which is basically the macroscopic fluctuation theory, which is again something that was done very recently in the last few months. Basically, you write down a probability of observing a history of fields. So density, magnetization, current, density current, magnetization current, and this variable k, which keeps track of the asymmetry between the plus and minus factors. And so there are some scalings that have to be done in order. So if I just go back, just to give you an indication of why you need to scale, because you have different noises which scale in different ways. So if you provide another scaling after the diffusive rescaling of time scales with some tumbling rate, and x, the space scales with some other scaling function ls, which is a distance. Then you are able to bring all the noise terms to basically the same strength, and so you can now write a path integral for that. So that's why you need to do a scaling with a second scaling. So I just want to point out, you do a first rescaling, which is basically diffusive, that gives you hydrodynamic equations. And in order to make all the noise terms of equal magnitude, you do a second rescaling. And again, so this was done recently in a recent study. So once you do that, you can write down an action for the history of these fields. So so this is sort of, we'll go into a large deviation function. This will be the action to observe a history of fields, density, magnetization, and current fields. And because we know the correlations between the noise terms, you can write the action. It can be written in two parts. One of them is for the fluctuations, and another one is for that non-conservative noise that I was talking about. So the Gaussian fluctuations are simply related by the correlation matrix that I was saying. So just to remind you, sigma rho and sigma m, let me just go back, are given by these, which is sort of conjectured by an exact mapping to the ABC model. And so you basically have a correlation matrix which couples the conservative part of the currents. But now you have this non-conservative part, which is basically Poissonian. And you can write a large deviation function for this Poissonian variable, which is exactly the same as a large deviation form for a biased random walker. So you can now add these two large deviation functions together and write an action. So this is again work done recently by Professor Kafri. So now, using this framework, you can ask many questions, because now you have an action formulation. You can start to ask questions about what is the integrated current flowing through the origin, for example. So that's something that we are interested in. So for the rest of my talk, I will describe how we compute this particular quantity, the time integrated current, which is very useful to understand the large-scale diffusive behavior of many systems. And of course, it was sort of started by certain paper by Derrida and Gershenfeld, where they were looking at this particular quantity, and then you can derive it in the hydrodynamic limit in many systems, including the symmetric simple exclusion process. But now we have two fields. So we can now define two different kinds of currents. So you can define integrated density current and an integrated magnetization current, and defined as follows. So LS was that scaling I had the second rescaling that I had done. Now the system size is from 0 to LS. And so now you're just asking for how much is the difference in density in half the system. So you integrate the density from LS by 2 to LS at a given time t, and you subtract the exact same quantity at time 0. So that tells you how much current has flown from the left half of the system to the right half of the system in time t. So this is the quantity that we are concerned with. Similarly, you can do the exact same thing for the magnetization. So this is why it's called the integrated current. And so this quantity measures the total flux of particles across the origin. QM measures the flux of excess particles across the origin up to a time t. Of course, this will also have terms which are coming from flipping. So you can have magnetization that is changing because of the flipping terms in half of the system. Okay. So for the rest of this talk, I will focus on quenched initial conditions, where you basically start with the step initial condition of this sort. On the left half of the origin, you have a density rho b. On the right half of the origin, you have a density rho a. And similarly, you can have unequal boundary conditions for the matter. Yes, please. Yes.
Right? I mean, how to define the current? I mean, it's not clear to me.
Yeah, no, so it is not conserved, but you can still define it in this particular way. Yeah. So that's what we are saying. It's not.
No, then it's not current. I mean, something. That,
yeah.
But well.
It is a current plus some non-conservative. You're absolutely right. Yeah. So yeah, so we start with these boundary conditions, which are again well studied in the literature in the context of simple symmetric exclusion process and other known models. So we can now write down using that a large deviation function for the quantity that we are interested in. So let's start with the large deviation function, which is basically the generating function for the integrated current. The way you write it is, because we had an action, you can actually write down this action and a biased action, which will then give you the generating function for the quantity that you're interested in. And of course, you have to also respect at the microscopic scale the continuity equations. So here you have a continuity equation for the density field, continuity equation for the magnetization field. And as you can see, there's also a non-conservative term. And so you have to now evaluate this quantity. And you can convert the action into, so by imposing auxiliary fields that impose this constraint, you can convert this into an action. So again, this is standard macroscopic fluctuation theory, but in this case, you have to do it for two different fields. So here you get the full action with this Hamiltonian density. This is basically taking the action that I was writing down previously and imposing these Lagrange multipliers and getting this Hamiltonian density. And so these are, once you have the action, you have to write down the Euler-Lagrange equations that tell you the typical currents. Again, this was done very recently by this group. And these are the bulk equations. They look daunting, but these are the equations that will then give you the typical solutions for the density and the currents in this model. So once you have this, you can start to calculate the large deviation function that I was asking. Just in order to calculate that, you have to impose some boundary conditions. So the boundary conditions for the auxiliary fields, if you are computing, for example, the density current, is that the P, that is the auxiliary field that is conjugate to the density, has to have this sort of step initial condition at the final time, whereas the magnetization field is 0, and exactly the opposite if you're computing the magnetization current. And the generating function, of course, has this large deviation form, and we can, using the fact that we know what the large deviation function is, if we compute it, we can then compute all the cumulants of the current, or the moments of the current. Yeah, so that's what we're going to do. Once we have this function, we can then compute the cumulant. We will do it to the second cumulant. And so how do you do such a thing? Of course, it's very complicated. One way to do, I'll just go back one slide. If you can compute the exact cumulant generating function of the large deviation function, then you have all the cumulants. And that can be done in some cases, for example, in the symmetric simple exclusion process, but in most cases you cannot. So you have to create a perturbative method in order to extract the cumulants of this system. So this was work that was sort of pioneered by Paul Krapewski, who's in the audience as well, where you take the hydrodynamic solutions that you have for the Euler-Lagrange equations and then do a perturbation expansion. So for small fluctuations of the average current, you can expand the fields, the density and the magnetization fields about the hydrodynamic solutions with some perturbation parameter lambda at every order in the standard perturbation expansion. And the fields, and so you have rho naught and m naught would correspond to the zero, sorry, not the zero, but the hydrodynamic solutions. And in that case, because there are no fluctuations, then the p variable at that order is 0, right? And so the fields, for example, as the first order, as the 0th order equation would just be this, which is basically the original hydrodynamic equation that I wrote down in the first slide. So the perturbation expansion will then also provide for you the equations that govern the higher order terms. So for our purposes, it's sufficient to go up to first order. Yes.
I just missed what is lambda?
Lambda is a perturbation parameter. It is the bias. Yeah, lambda. So let me, yeah, exactly, in the large deviation function. So here, this one. Yeah, you're computing that large deviation function, so you just put that at the conjugate. And so you can now do this expansion, and now you can get fields at 0th order, fields at first order. And the general technique that people have been following is, if you do the perturbation framework, is to solve the first 0th order equations and input them into the first order equations and then derive the currents. So, again, because you have the boundary conditions on the Q and the rho variables, you can simply translate it at every order. And so these are the boundary conditions that the first order fields would translate to. And of course, this is work sort of pioneered by Krapewski and Mearson. So we are just following that technique in order to extract it, but now with two coupled fields. Yeah, so here we will basically also now do a perturbation expansion, assuming that the currents themselves have a perturbation expansion. So once you have a perturbation expansion for the currents, you can write down these very nice looking equations, very similar to work done by Rahul recently, where you can write down time integrated currents and the first cumulants and the second cumulants as well, based on, so you'll notice something very nice, that if you were to compute the first cumulant, you would just have the 0th order fields. And if you were to compute the second cumulants, you would have the first order fields. And this gives you a very nice way to compute it. So now the question is, how do you calculate this large deviation function? And this is a bit involved, but you can write down the large deviation function as a perturbation expansion as well. And so that's what we do. Here we write it down as some large deviation function, which is the current that would be predicted by the 0th order fields, and currents that would be predicted by the 1st order fields, and some coupling terms. So this is slightly different from the simple symmetric exclusion process. If you follow the same machinery for the simple symmetric exclusion process, you end up with just this term. Of course, this is a matrix equation. It has couplings between the different density P fields. But in addition to this, so this just gets generalized to a 2x2 coupling. But in addition to this, we find a very interesting term here. So sorry, this is given right at the end here. So we find a term that is exclusively P squared that doesn't appear in the simple symmetric exclusion process. Yes, please. Yeah, so this is the 1st order, 2nd order, and so on expansions. So here, so P rho can be written as rho naught plus this perturbation parameter rho 1 plus higher order terms, right? And so, and then all you have to do is take these equations and put them back into these very daunting looking bulk equations, which are the coupled Euler-Lagrange equations for this action. And now just do a perturbation expansion at every order. So at the 0th order, you expect, so at the 0th order, you expect the original hydrodynamic equations to reappear. So that's what happens because the P fields are 0. P basically gives you the conjugate to how much the fluctuations are. And at the 1st order, you get this. Again, looks quite complicated, but now we should be able to sort of solve it step by step. So that's what we will do. So in the last 10 minutes of my talk, I will explain how we solve it for a certain initial condition. Although I showed you this general step initial condition, we can actually solve this analytically for the flat initial condition, and I'll show you results for that. And so this is what the 1st order solutions. Sorry, yes, please.
Up to the lambda square order.
Yes.
The entire. Okay.
Yes, absolutely correct. Yeah. Up to lambda squared. Higher order terms are harder to get. So this equation that I'm showing you here is, oops, sorry. This equation I'm showing you here is correct up to lambda squared order. And so we can now use this framework to derive the cumulants. And so just to complete the story, we can also, once we do the expansion of the cumulant generating function, you can relate, this is the derivation of the equation I was showing before. You can relate the second cumulant to basically Q, which is the integrated current at the 1st order minus this term. And I will just show you the final result. We obtain this as the final result. So this is our analytic expression for the cumulant of the just the density current at this point. We are going to compute, but you can write it down exactly for the density and magnetization current, and you have this extra term, as I was saying. It just appears as an effect of activity, and this would be the effect of just fluctuations. So for example, if you were to put D, the diffusion constant, to 0, yes, please.
Missed something. So I mean, what is the large deviation from? Because I mean, isn't it that all cumulants scale with T?
Yeah. So we don't make that assumption that it scales with T. It scales as a function of T. We are not pulling out a T here. It is psi lambda comma T. It could be any.
But usually the large deviation form is. But so what is the finally what is the large deviation?
Yeah. So it has many different T behaviors, which we can extract. I will show you that. Yes, please.
Without the scaling, how would you justify the saddle point then?
Saddle point of this.
Usually you rescale and bring a large time parameter in front of the action.
Yes.
And then you can justify your saddle point.
That's a good question. Yeah. So I suppose we justify it as T is large enough, but we don't have a scaling that comes out. It is some T to the power alpha, which is what we see. We see square root T at short times, square root T at large times. You can pull it out.
T to the power alpha, you can do a scaling of the action. So it's,
yes, we should be able to. Yeah, we should be
able.
Yeah. So we do actually integrate out these. We do a T scaling at the end. We'll show you. Once you have this expression, you can do a T scale. That's what we get. And so that would be the justification. It's large enough time for you to be able to scale. But what it is, what the alpha is, that depends on the expression. Yeah, so here's how we extract the scaling behavior. So once you have these equations, so once you have these equations, we're just going to solve it for the flat initial conditions. What we do is we start with uniform density and zero magnetization everywhere. So this zero magnetization throughout the lattice. So what that does for us is allows us to solve the zeroth order equations really easily. So we notice that the zeroth order equations themselves are nonlinear. The hydrodynamic equations are nonlinear, they're coupled and nonlinear. So you cannot really solve them. So you have to find some special cases where the hydrodynamic equations themselves are soluble. So here is a trivial case, which is flat density and zero magnetization. So once you have this is basically the solution at all times. It doesn't change. You can put this back into your first order equations. This is what it looks like. And now these can be solved. You just diagonalize and get the solution. So I won't go through the way we solve it. Of course, you can just do a matrix diagonalization, but I'll just show you that we have this quantity G, which is basically Peclet number squared times this interesting function of density, which is very useful. It is exactly what comes in the correlation function calculations that were done previously in previous studies. And here are the full solutions to the fields. So you can write down exactly what the P fields look like in Fourier space and M fields look like in Fourier space, and with some initial conditions. So once you have this, all you have to do is put this back into the formula. So I'll just show you. We can convert our exact equation that we had in real space into an expression in Fourier space. And so here I haven't done any t-scaling yet. This is what the second cumulant would look like. Now we want to extract the t-scaling. So this is the final expression that we need to extract. Is that clear, Abhishek? So that question that you asked. So here now, if whatever t-scaling comes out of this expression is the t-scaling. Yes. Which equation?
Equation for two fields. Just the equation to the leading order of the two fields that you solve.
This one.
This is the leading order.
This is the leading order.
Okay.
Yeah.
And
once you make the assumption that you have flat initial conditions, these simplify greatly. Okay.
for the flat
initial conditions.
Okay.
Absolutely. Yeah. So flat initial conditions, these simplify a lot into these equations. That's all you need to solve, and which we can solve, which is a simple exercise in matrix diagonalization. So now all we have to do is put this back in here and extract the scaling forms. Yes.
Cumulants are not of the same order. How can you pull out a t to the power alpha? And how
No,
do you know that all other cumulants are also in the same order?
That's a good question. So this is not because it's not scaling with t. If you bias it, this would have some t scaling. This has another t scaling because it is a second order cumulant. We don't know what the higher order cumulants are going to be. That's an absolutely good question. In the sense, does the full large deviation function scale with t? That we haven't checked. But yeah, up to second order. So this is not scaling with t. This is also some square root t. And this would also be some square root t. And so, yeah, so using this exact expression, I won't go through the math. We can just actually write down some scaling functions, which will allow us to extract the second cumulant of the integrated density current. So we find that this function, so this function that we wrote down, this f, which is the Fourier space expression. If I go back one slide, this whole thing can be written as a Fourier space f of k of t, which we write here, which has some very nice forms, which can all be sort of, these are exact forms which we can write down. All we need to do is now extract the scaling. And so we can just show that this has some scaling form with some scaling variable u is equal to k square root t. And we have this nice scaling form. And so of course, this implies that the second cumulant would grow as square root t. As you can see, this prefactor that we have here has very interesting effects of density, as well as now once you integrate this, you get the Peclet number as well, where this is the scaling form. And similarly, at large times, we can do the same scaling analysis, but with a different scaling form now, and you can extract again a square root t behavior. So the small time behavior and the large time behavior can be extracted as square root t. So let me show you what we have as a final result. So finally, after performing the scaling analysis of that big expression, you get the second cumulant of the density current goes as square root t times the sigma rho, which is basically the correlations in the density fields divided by square root 2 pi. This is exactly the same result that you get in the simple symmetric simple exclusion process. Yes, please. No, so this is not scaled with the system. Yeah, this is proper time. I mean, this expression you can unscale. I mean, in the sense that right now I performed a gamma t scaling. First you diffusively rescale, then you do a gamma t scaling, but now you can unscale it and match with simulations, for example. The system size enters here in the T. Yeah. I mean, but like at different system sizes, you can match them with different rescale times. So this is okay. In this case, this is scale time. I will show you results for unscale time as well. Yeah, this is scale time. Yeah, I can show you results, but the unscaling is not so hard in this case. Why not? Yeah. But t tend to 0 you can have as proper time as well. Okay. So at small times you have the square root t behavior. So basically what happens is this whole process is governed just by the fluctuations in density at very short times. And in the large time, we have this very non-trivial looking result, which is you have the simple symmetric simple exclusion result modified by activity and density in this way. And G is that function that I'd shown you before, which basically defines the correlation length in the fluctuating hydrodynamics framework. And so we see something very interesting. As you approach the critical point, the fluctuations seem to diverge with this correlation length, and they also have this non-trivial dependence on the activity and density. Yes, fine. Yeah, so this is what we would get. And now we would like to compare it with other known results. For example, Satya, Alberto, Gregory recently did some work on non-interacting RTP particles, which which had zero diffusion in it. So yes.
So I guess if it scales like square root of t, the large division function can still scale like t, right? Because if you just lambda by t, if you define as a, because you are in lambda, right? So lambda by t, if you define as a variable, or lambda times t, or something like that. So then the quadratic term can give still square root of t, right? So t times whatever 1 by t square or something like that. I mean, one has to see properly,
yeah, but what we see is that between these two, it scales with a different power of t. So that's something that we are still working out. So it scales a square root t at very short time, square root t at very large time. In the middle, I'll just show you in the next slide. Yeah? Okay. And so this is what we see. And since I'm running short of time, we can also do the whole analysis for the case of zero diffusion, where in this case now there's no noise. The only noise comes from the flipping. And we can do the same thing for the flat initial profiles and can go through the result. And we finally get these expressions for the second cumulant in the zero diffusion case, but with interactions. And we can now take the non-interacting limit, which is basically taking the density going to 0. And we're able to match with the results derived by Satya et al. In for the short time limit, but sorry, in the large time limit. But in the short time limit, we see a t squared behavior for this cumulant, which is different from the non-interacting case, which is sort of an interesting property of exclusion that is being seen in this model. But we are still trying to understand the main differences between this. It could also be from quenched initial conditions versus annealed initial conditions. We're looking into that. So yeah, so now I'll just show you some results from numerical simulations and our predictions. So you can, of course, now take the model with the rules that I've defined and do microscopic simulations. And this is exact microscope. So these are the exact integrated solutions to the non-linear hydrodynamic equations at 0th order. And of course, they match very well, as was seen in previous studies, with the microscopic simulations that you do on the lattice. Then here is something that we can do with the microscopic model, where we can compute the second cumulant of the density current, second cumulant of the magnetization current, and we can sort of match it with the square root t behavior. And we can only do relatively short times in our simulations, so we can't really see what happened at very large times with the simulations, but they match very well with our predictions. And of course, you can also do it at finite lattice sizes and numerically integrate the equations, the hydrodynamic equations at every order, and get predictions which also match, which I haven't shown here. So now I'll just show you theoretically what we would get if you were to go at much larger, look at this question at much larger times. You have interacting RTPs. This is what we are studying basically in this lattice model. And you have the result which matches with the symmetric simple exclusion process at very short times. And then you have this intermediate regime where the fluctuations are much larger than what is described by the simple symmetric exclusion process because of the flipping terms and the activity. And then it sort of saturates to another diffusive behavior at large enough times. And so this is again some diffusive behavior at of these interacting particles, but they are suppressed in comparison to what you would see for non-interacting RTPs, which is the effect of exclusion. Then sort of we can also use our analytic results to understand what the effects of density would be. So initially, so in the symmetric simple exclusion process, the cumulants of the currents depends in a manner rho into 1 minus rho. That is, if you were to take a density rho and you were to take a density 1 minus rho, which is the same, you would get the same answer. So here's, for example, yeah, just in 2 minutes, take a density 0.1, it should match exactly with density 0.9 in the simple symmetric exclusion process. So here in the interacting RTP case or in the interacting lattice model, you see that they actually do match at short times. But then as you increase time, they saturate to two different diffusive limits. And so that's something that is an effect of activity and density as well. Finally, sorry, yeah. So finally, I'd like to show you the effect of the diffusion constant. You can actually now decrease the diffusion constant of the system. That is, disallow interchanges between particles. And you, of course, see a large time square root T behavior emerging, but you also, because we had this 3 different regimes, there's a short time square root T behavior, which sort of gets suppressed, and it sort of gives rise to this T squared behavior that I was talking about in the 0 diffusion limit. And so you can also study this. And we can match these very short times with simulations as well. So just in conclusion, we studied the current fluctuations in an interacting active lattice gas that allows a comparison between microscopic measurements and predictions based on a fluctuating hydrodynamic theory. We used MFT to compute the cumulants, the time integrated current through the origin up to the second cumulant. This is possible because of a perturbative approach, which we just applied. We found the long time variance diverges at the critical point. That's something that we would like to study further. 0 diffusivity limit of this model has interesting similarities with this 0 diffusive case of the non-interacting run-and-tumble particles, but also shows differences because of exclusion. And as an outlook, it would be useful to find situations where we can solve the problem for not just flat initial conditions, because in other models, you can show how even the first cumulant has a square root T dependence because of different initial conditions. It would be interesting to analyze how this current behaves close to and beyond the phase boundary. And of course, a natural question to ask would be, what is the difference between quenched and annealed settings in this problem? And finally, there are other models which have coupled fields, which are also amenable to fluctuating hydrodynamic equations, like the light heavy model, which we plan to explore in the future. And thank you. And I would like to congratulate Deepak for his great honor. Yeah.
Thank you, Kabir. Questions? Just wait for the mic. Okay, you have one.
So can you please go back to your slide where you presented your microscopic simulation? No, before, yeah, this one. So no, I'm just wondering about the time unit. What is the x-axis? This is a proper time or?
This is actual time.
No, but then t tending to 0. I mean, small t behavior. I mean, what does it mean? I mean, why you would be interested in t so small? I mean,
it's a quantity we can measure, and it corresponds to the limit of the where activity is not playing a role yet. That's why. That's the reason. Yeah. Sorry.
The scale time, I think, yeah, it must be scale time.
But we can unscale it as well. In the sense, this is the unit. We can do the whole calculation. So if I want to show you these equations, for example, we can do all the calculations in the unscaled units, for example, here. And we can work out all the quantities in unscaled time as well. No, that's just a simple scaling.
No, okay. So let us forget about the, theory. So, simulation, see, your time scales or the rates you have scaled such a way, it has a diffusive time scales L square, dilation time L square. So
Yes.
now, I mean, there are time scale is
That's the
1.
question. Yeah. So diffusive time.
Right, diffusion sets at your
diffusive.
time unit. So this is scale 1, and that's L square. So
That's
now,
correct.
I mean, T tending to 0. I mean, well, first of all, of course you can take, but T tending to 0, it's a dimensional thing. I mean, first of all, why would you be interested in T tending to 0, proper time limit? So I think it must be scaled.
Yeah, this is scaled with the diffusory scale. You're right.
Then the next question is that if you take large time limit, well, large compared to what? So
yeah, so large compared to, for example, gamma inverse, which is basically a time scale. That is the
L
flipping.
square, that is L square. I mean, large
No,
compared to
gamma
L
is
square
different
time
from
scale.
L. Gamma is different from L. L is the lattice scale.
You have scaled gamma, right? Gamma is 1 by L square. The model, as far as
that is true. Gamma, which is basically without scaling gamma, you're going to get different effects of activity and different.
Right. But you have, I mean, from the beginning in your model or microscopic simulation, you have taken gamma of order 1 by L square.
Yes.
So that means that your relaxation scales, I mean, you have, it's L square. So one scale is 1, another scale is L square. So now you'll have to say, I mean, what is small time and what is large time compared to this? I mean, so I mean, one thing is that much smaller than L square, then other scale is much larger than L square. So what do you mean by much smaller than 1? Well, you can of course define, but that, I mean, I don't know. I mean, that does not make sense to me.
Sure, we can discuss.
Yeah. Okay, there's another question there.
So I have a very simple question. Like, if you go back to the hydrodynamic equations you wrote in the fluctuating hydrodynamic equations you wrote in the very beginning. So like, how do you put the noises? It has some specific form, and also the strengths are like dependent on the parameters of your lattice, your microscopic lattice model, right? So is there a simple way to understand why you put the noises in that? Yes. No.
Yeah, this is conjectured through a mapping to the ABC model. So the ABC model, you can actually write down what the noise terms are. And so these forms are given by a mapping to the ABC model. So that's the way that this noise is written.
More questions? Are there questions from people joining online? Please unmute yourself and you can ask a question. Okay.
Yeah.
Oh, Sanjib. After Sanjib.
So this square root of t is only for the flat one, right? The
Yes.
moment you put some bias, then it will become t, I guess, right? The cumulant, second cumulant or something, no?
No. In the SSCP, it's still square root of t, but it has a very nice dependence.
No. I'm saying
in our case,
if you put a fish,
so that's
like
this probably goes to t in this case because of activity. But in SSCP, for example, if you have non-flat initial conditions, it's still square root t, but with rho a plus rho b instead. Yes. One second.
Okay. So if you say that the noise is in the same form as the noise strength are of the same form as ABC model, this model you are studying must have some relation with the ABC model on mapping, right? Where is the mapping?
Yeah, so I don't have that exact sort of where the hydrodynamic equations of this model become the ABC model. I'm not sure. We'll have to check.
So this is the assumption.
No. So the mapping is clear in the sense that one species of particles is A, one species of particles is B, which.
But the ABC dynamics is different than the model. The dynamics.
No, so the dynamics is D, which will basically tell you the interchange of A and B, and B and C interchange would also be D in this case. And the bias would just be lambda, just like the ABC model. So the mapping is clear, but how the hydrodynamic equations are derived, that's something that I have to check.
Oh, maybe you can talk later.
So this tumbling noise that you have, usually if you consider a single particle, then in the large T limit, they behave like Gaussian noises.
Yes.
Now here, because of the scaling of the gamma, they still behave like Poissonian statistics in the hydrodynamics.
Yes, absolutely. Yeah. So, very good point. Exactly. Yeah.
Okay. So with that, let's thank Kabir once more for the nice talk.